So guys, we're just about to start, but before that, tomorrow, for those who can, we are organizing an informal visit to the synchrotron laboratory, so if you want to know the synchrotron accelerator in Campinas, and you'll have the opportunity to be there, you are all invited. Unfortunately, we don't have a bus to take you there, so you have to take care of yourselves and be there at 10 a.m. If you want to go, I'm just passing a paper, just put your name, email, and institution. We need this to let you enter the campus. So just circle it around, please.
So good afternoon, everybody. Now we're going to start our last but not least section, third section here. We're going to talk now about, until now we talked about the life in the past and its discovery and its emergence. Now it's going to be the part that we talk about life as we expect it in the future to see in the context of extraterrestrial planets. Now this section we're going to talk about the applicability of life in extraterrestrial context, biosignatures, and anything related to this and how we expect to search this kind of life. Okay, we're going to have three lectures now. First one, Professor Gustavo Porter Mello. He's a BSc in astronomy from Federal University of Rio de Janeiro. He is PhD in astrophysics by National Observatory, and now he's currently the professor of Federal University of Rio de Janeiro in the Observatory of Belo.
Try to focus on what can be said about early conditions on the Earth as we consider conditions of the early sun as judged by its proxies with other stars, young stars that may represent what the sun was doing at the time that the life arose on planet Earth. So this is part of our team. We have many collaborators in Europe, the United States, some PhD students and even undergrads. So I'll be introducing the concept of the habitable zone, or the theory or model of planetary habitability, and new frontiers and details concerning stellar high-energy emissions. So the habitable zone is a very important concept, perhaps the most important concept in astrobiology, because it really does a good job in unifying everyone. Everyone meets at the habitable zone because physicists and chemists and biologists and planetary scientists and even cosmologists, they have something to say about the orthodox concept of the habitable zone. Of course, we'll be talking about the classical water-based habitable zone. You can have your own habitable zone for other fluids, say methane or ammonia, you name it. You can define your own habitable zones. And you can also define habitable zone by way of not having the liquid at the surface, but by having subsurface oceans. We'll be talking none of that. We'll be just focusing on the traditional and orthodox theory that puts liquid water at the surface of the planet. So this is the classical, the really orthodox concept of the habitable zone. You demand liquid water at the planetary surface, and this of course defines a range of distances around any star. Even substellar objects, even brown dwarfs may have habitable zones. So there is a range of distances around the star in which a planet can hold water on its surface. Of course, this is going to depend, to be contingent upon properties of the star, mainly luminosity and the speed of evolution. Of course, the more luminous, the more energy the star gives away, the farther away from the star the habitable zone is going to be. And also planetary properties, like size, mass, chemical composition, and details upon evolution. So there's lots of dimensions and details and fine print about the habitable zone, but we are going essentially to cross over all of that to focus on the main aspects so that we can discuss some of the new dimensions and newest results about stellar high energy emissions and their influence upon the habitable zone. Okay, so we define the habitable zone as a range of distances, of course thinking about a range of temperature for liquid water. So the planet has, as an average, has to have a temperature above freezing and below boiling. This has been known in astrobiology for many decades now as the Goldilocks theorem. That's probably a story that everyone knows about. In Brazilian Portuguese, cachinhos dourados. So you want to strike in the middle. Too hot is bad, too cold is bad. You really need average properties average physical properties that can allow the presence of liquid water. And there's a lot of fine print in the contract that people usually are not worrying about. Things like chemical composition of the planet. So a planet born at different times in the history of a galaxy is going to have different chemical composition. So the rate of lithosphere to mantle and to core, as well as the composition of the atmosphere, may change. And this is going to change the definition of the habitable zone. The presence of a magnetic field, plate tectonics, the internal heating that comes from radioactivity, the abundance of these nuclei changes with time. Also the distribution of continental masses, and lots of really complicated details that we don't have time to discuss about. Also, we are going to apply this concept to our own solar system, and of course to extrasolar systems as well. In our own solar system, we have two nice Earth-like planets, which are the Earth and Venus, and we also have Mars, which is much smaller. What we don't have is a super Earth. There's nothing in mass between the Earth and the next most massive planet, Uranus. There's nothing in between. And we know these super Earths are very, very common in the universe. So we may be talking, if you go into the theory of super Earths, about super habitable planets. Planets that are big, they are bigger than the Earth, they are very resistant to aggression from the outside, like impacts, supernova explosions, they are resistant to this stuff. And we don't have examples in our own solar system to apply this concept. But we can apply the theory to Earth, Venus, and Mars. So we are going to think about the Goldilocks theorem and try to search about the mechanisms and distances that can keep liquid water on the surface of a planet. This is the main equation. It just considers the energy that is reaching the planet in terms of the SF, the effective flux, which the flux the Earth receives now from the Sun. And this quantity changes with time, because in the past the Sun was weaker and less luminous than it is now. So this energy is thermalized, is spread over the surface of the planet that reaches a black body temperature, and it starts emitting in the infrared. So we know there is also the greenhouse effect, because the atmosphere is transparent to the visible radiation, but it's opaque in the infrared. So this temperature must be increased by the greenhouse effect, which comes from many gases like CO2, water vapor, methane, and others. The number 4 here appears because the planet collects energy as a disk, but this energy is averaged over the surface. So we have 4 pi squared. So the number 4 appears here. And this is the main stabilizing effect. This is the real question of nowadays. That's climate change. That's the greenhouse effect. That's the action of CO2. As the temperature increases, the partial pressure of CO2 decreases. It's a stabilizing effect. This is a stabilizing mechanism that allows liquid water to exist in a range of distances. And the essential physical coupling here is weathering, that is the consumption of new rock, the chemical attack by water and acids over new rock, the concentration of CO2, also water vapor, and the stellar luminosity that is constantly evolving. So we have to consider the dynamical dimension of the habitable zone. The sun is getting brighter, so the habitable zone is moving outward. And this is the main destabilizing effect, because as temperature increases, the partial pressure of water vapor also increases, and it is a greenhouse effect gas. So it tends to destabilize the CO2 effect, but there is also a compensatory effect bundled inside the action of water vapor, because as water vapor pressure increases, more clouds are formed, and the clouds are highly reflective, so they help to cool the planet. So this is a destabilizing effect with a partial stabilizing effect inside. And the main stabilizing effect is as temperature rises, CO2 is removed from the atmosphere in a dynamical cycle. Oh, sorry. This is really sensitive. So this is our present understanding of the mechanism. Many details are not entirely clear, but we know that we need a planet with volcanism, an active, geologically active planet. Volcanoes emit many gases, also CO2. It has a very small concentration nowadays on the Earth, but it's an almost fixed concentration. Water vapor, of course, varies a lot during the day, but CO2 is the main actor in climate change and the greenhouse effect because it has this constant concentration that is always working. So as CO2 is released and the planet heats, the action of liquid water is increased. It dissolves CO2, creating a weak acid, which is carbonic acid, that removes silica and locks carbon away in mineral compounds. These sediments are carried to the sea, where marine animals use these sediments to make shells and other body parts. When they die, all of these sediments are laid down at the bottom of the ocean. Life does not have to be present for this to work. This mechanism is abiotic. It can also work in the absence of life. And eventually, because the planet is active geologically, these sediments will find the subduction zone. They will be changed back into the gaseous phase and released again as volcanic vents. So as CO2 increases, the mechanism that removes CO2 also increases in efficiency. As CO2 is removed from the atmosphere, the mechanism loses efficiency, and CO2 can also accumulate in the atmosphere. So this is a regulating mechanism that is able to set the range of distances for which liquid water could exist at the planet's surface. We have 3 nice rocky planets in the solar system to test this model. If it does not explain these planets, it goes straight to the recycle bin. But luckily it does explain more or less what we are observing. We know that Venus is much hotter, has a much higher atmospheric pressure than the Earth. This is the average temperature of the Earth, considering the greenhouse effect. And Mars, of course, is much smaller, has a much thinner atmosphere, and is a much cooler planet. So as we consider the mechanism, we can show that the inner limit, that is the closest the planet may get to the sun, and still be habitable, still be able to maintain liquid water at the surface, in terms of the flux that the Earth receives today, is just a few percent. Past this limit, water vapor will reach such a saturation state in the atmosphere that the stratosphere that's normally dry will become wet, and the photons, the UV photons from the sun, will begin to photolize the water, and you are losing the oceans. Initially, very slowly, but as the luminosity of the star increases, much faster. As you get to 1.4 or 1.5 times what the Earth receives today, the oceans get lost, they get evaporated in a very short time scale. So the planet cannot be submitted to more than, say, 40 or 50% excess flux before it really starts to lose its oceans. Venus lies inside this limit, so by our model, Venus never was habitable, which more or less explains well what we observe. Venus apparently never had a chance. It was always or at the limit or inside the inner limit of the habitable zone. So as we turn to the outer limits, we don't have to worry much about water vapor because the planet is getting cooler and cooler because it's receiving less energy from the star, the sun in our case, and to the point that because of low temperature and the lower action of water, CO2 accumulates in the atmosphere, and the planet gets more and more of a greenhouse effect until a point where there is no point in increasing CO2 because the atmosphere is opaque to infrared radiation. So all the heat is being held back at the surface and the planet can get no warmer. We reach this point when the effective flux received by the planet is around 1/3 of what the Earth receives nowadays from the sun. This is probably too pessimistic because we know that Mars lies inside these limits. No, sorry, actually Mars lies slightly outside this limit, and still Mars was able to hold on to liquid water in the past. So this model is probably insufficiently optimistic. It does not do a very good job of explaining Mars. Mars probably was habitable, at least for some part of this evolution. And the real problem with Mars is not position. The real problem with Mars is size, because it's too small a planet, it loses heat too fast, so it loses tectonics and volcanism, and cannot hold on to its magnetic field or water and atmosphere. So the real problem with Mars appears to be not position, but actually size. If the Earth was placed at the position of Mars, the Earth very probably would still be habitable. But if Mars was placed at the position of the Earth, it would still become uninhabitable in a relatively short time scale. Of course, we can, and we want to, apply these concepts to extrasolar planets, to exoplanets. So from the vantage point of space, as we observe Venus, Earth, and Mars, of course we see a very strong absorption line of CO2. That's part of the greenhouse effect that you are seeing right now, absorption in the infrared by the molecule of CO2. But in the case of the Earth, we are also seeing water and ozone. And ozone, of course, comes from oxygen. It comes from photosynthesis. And perhaps some methane signature as well. So say, in the next few years, with the James Webb Space Telescope or other space hardware, sufficiently powerful so that we can actually image an extrasolar planet, and you start seeing something like this, you see CO2 and ozone and methane and water, very probably you have just detected photosynthetic life. It actually may be much easier to detect photosynthetic life in an extrasolar planet than say on Mars, because on Mars, obviously, life is not at the surface. You have to dig underground, you have to do really a survey, but in this case we are watching a planet that has been massively modified thermodynamically in its atmosphere by the action of life. Of course, there is the possibility of some false signal. Say, if a planet is in a runaway greenhouse, losing its ocean, the water is being photolyzed in the atmosphere, and we are going to see some signal for ozone and oxygen. So the planet may actually be dying, and we're just watching its death throes. It's actually on the way to become uninhabitable. Also, very small and frozen planets, without O2 sinks, the oxygen cannot interact with the surface. It might be able to accumulate oxygen abiotically. So maybe you are going to watch a signal for ozone and oxygen, and it's not originated in life. But apart from these possible false alarms, most planetary scientists are confident that in the next few years or so, if you do detect a planetary signature like this one, you probably have detected photosynthetic life, and really we will be able to test, to extend this model to other planets outside our own solar system. So this is the introduction to the orthodox, the classical definition of the habitable zone. We are now turning our attention to one of the many dimensions of the habitable zone that is being recently, it's gaining more and more attention as we realize that its importance may be really, really crucial in determining the habitability of planets around low mass stars, less massive than the Sun, and small planets like Mars. And probably small planets like Mars are much more common in the universe than big planets like the Earth. Also, we know from astronomy that low mass stars, undermassive with respect to the Sun, are much more common than stars like the Sun. And the common feature of all low mass stars is that they have convection at the surface. So we have plasma in movement. As the star rotates, it presents differential rotation. So you have convection of a plasma with differential rotation. You have a plasma moving around, generating magnetic fields. So these stars, they generate and amplify magnetic fields, and this energy, the conversion of mechanical energy into magnetic energy, is later converted in thermal energy at the surface, photons and winds. So this energy is dissipated at the surface of the star as spots, like we observe in the Sun. We all know the 11-year cycle of the Sun of high magnetic activity and low magnetic activity. So this is the really strong Sun, the active Sun. So we have winds, particles being ejected away, also far UV and UV photons in the far ultraviolet, and also X-ray. These emissions, they evolve, decaying exponentially with time, because as the star is rotating, it's generating magnetic energy, but the winds carry away angular momentum. So the star spins down really quickly. So this really high energy phase for the Sun, it doesn't last very long, at most a few tens of million years. So we really know from observing nearby stars in different stages of evolution. This, for example, is the solar twin our team has discovered, and it has essentially the same level of magnetic activity as the Sun. We see that rotation decays exponentially, and so the high energy emissions they decay as well. This is the project The Sun in Time. We try to find nearby stars with high fluxes and high quality data with the same mass and chemical composition as the Sun, so that these stars would have the same convection properties. So we can trace the behavior of high energy emissions only in the variable time. So this is the Sun in Time project. These are cartoons and visualizations of what the real stars might look like. So as the star ages, it very quickly loses this high energy character and becomes an old and inactive star, a quiet star like the Sun. So this is a common feature for every single low mass star. Every star like the Sun or less massive than the Sun, they undergo a phase like this. So we see if you watch the spectrum of energy, many of you are biologists, the UVC that reaches the Earth's surface is a very dangerous radiation because it's biologically active. We are talking here about the far UV. There is much higher energy than the UVC. And we see these are the ages of the stars in giga years. So 100 million years, 300 million years. You see that very quickly the hardness of the X-rays decay with time. And also the total energy emitted in this high energy region, it decays very quickly with time. So one important feature of models for early life on the Earth is that the Sun was not like we observe today. The Sun in the past was much more active. Actually, probably it emitted winds, particle winds, 1,000 to 10,000 times stronger than today. X-rays 1,000 times, and the far UV up to 100 times more energy was deposited at the atmosphere of the Earth at that time. Actually, perhaps some of you are familiar with the faint young sun paradox. The Earth was not supposed to be habitable because the Sun was much fainter in the past. This might be a possible solution for the paradox, because if the Sun really was losing mass at a very high rate, the Sun was born not with one solar mass, it was slightly more massive, so slightly brighter. So this might solve your faint young sun paradox without you having to invoke exotic gases for greenhouse effect. This might be a solution according to some physicists. So this is a summing up. The early sun was much stronger in winds, much stronger in X-rays and UV and the far UV. So why is this important? After all, for the present sun, this is a very tiny fraction of the energy. And even for the very young sun, the total power emitted by the star is not that large. The problem is that the total power is not the whole history, because the process matters. These photons, they are really high energy. You can imagine yourself, say if you like wrestling, being punched by a small guy. Perhaps you can take 50 punches and nothing much is going to happen to you. But if you are punched by Mike Tyson, just one punch might be enough. And these photons, they are Mike Tysons. They are really energetic, then can ionize molecules, they become charged, and then the stellar wind carries the molecules away. They heat and expand the exosphere. Even though these photons are mostly thermalized in the high atmosphere, they are really injecting a high amount of power in the most fragile and less dense part of the atmosphere. Of course, magnetic fields can help you against particles, but not photons. So the mechanisms at work. Energetic emissions in photons promote photolysis. You have molecular dissociation in the atmosphere. So you have radicals that become active. Also, the X-ray and UV heats and expands the atmosphere. Ionized molecules are carried away by the wind, and it was 1,000 to 10,000 times stronger than we observe today. This was really important for Mars. Mars is a small planet that lost its magnetic field. It has suffered intense erosion of the atmosphere. It very probably had surface water in the long past, so its surface temperature was probably above freezing. But the core solidified, the magnetic field went away. Small planets cannot hold on to light molecules. Molecules simply escape into space. This might explain the loss of a total ocean in Mars as much as 10 meters deep. Say if you cover Mars with water up to a height of 10 meters, this mechanism can explain total loss of this amount of water. hydrogen escapes, oxygen oxidizes the ground, and also for Venus, this mechanism in the past might explain the loss of a full Earth ocean. So maybe in the deep past, the solar system had actually 3 habitable planets and not 1, as we observe today. So for, how much long do I have? Okay, that's what I need. So for the end of the talk, I'm going to present some interesting results about this star, Kappa Ceti. It's a very nearby star, very similar to the Sun. We have been studying this guy for more than 10 years now. And it's a near perfect match for what the Sun should be doing when life arose on Earth. It's about 600, 700 million years old, solar mass, almost the same chemical composition, but it's much younger. As we can see here in the emission of the calcium light, this is a proxy for the high energy emissions. You can see that the Sun and the solar twin are really quiet stars, and Kappa Ceti has, judging by this line, an age of perhaps 100 or 200 million years, but this is just a proxy. This is the near UV. It doesn't harm the surface. The real action is going on at the far UV and the X-rays. You can see that in the thermal regime, Kappa Ceti is actually weaker than the Sun, because it's cooler and less bright, it's less luminous. But in the far UV and the extreme UV, it can emit up to 10 to 20 times more energy. So in the thermal, it's actually less bright, but in the far UV and extreme UV, it's much brighter, and the wind is at least 60 times more stronger than the wind we observe on the Earth nowadays. So if you will indulge me in a flight of speculation, you might try to fathom what's the action of all these high energy photons and winds upon conditions on the early Earth. It's reasonable to assume that the atmosphere of the early Earth was at least mildly reducing, so it was reaching, say, CO2 and water vapor. Many of you have presented results on this this morning. Also perhaps methane. And these molecules, presumably rich in the atmosphere of the early Earth, they have photodissociation rates concentrated in the far UV. So in the far UV, it's a regime in which they interact the most with the stellar radiation. And the young Sun was presumably much stronger in this radiation than we observe today. So we have put together a photochemical model, and we found that the photodissociation rates and probably the rate of photochemistry going on at the atmosphere of the early Earth, at least at high altitude, was 20 to 10 times stronger than what you are going to get if you don't include the high energy emissions in your consideration for the early Sun. Many early models did not include the high energy emissions. They just assumed that the early Sun was just as bright as the present Sun. And we know that this is not correct. So if you do have some more photolysis and photodissociation, you might have some more interesting photochemistry going on. And, sorry? So, what do we do now? I need the last slide. Sorry, guys. I can do it, okay. So we are going to the last slide. This is, wow. Okay. Okay, association rates. Okay. So this is a proposition, a recent one, about trying to solve one of the really complicated problems about early life, which is the synthesis of nitrogenous base. The problem usually is ribose, which is very unstable and difficult to synthesize. So these authors have proposed to bypass this critical step in which you need to produce ribose by means of UV activation. So you can get canonical pyrimidines and nitrogenous base bypassing ribose and the attempt to generate ribose directly by means of far UV photons. So you might possibly conceive that in the early Earth, some action of these extra photons might just be helping life alone to really achieve some chemical pathways that are not obvious for the present Earth, but might be workable during the time when the Sun was much stronger in the high energy emissions. So I think I'm stopping here. I'm leaving you with the highlights of the talk, and I'll be happy to take any questions. Thank you.
Thank you, Professor Gustavo. Does anyone have any questions for him?
Michael, come on. Counting on you. You can throw stones at me, I don't mind. Just say something.
We've got the notice, so I really like it. So congratulations on a great lecture. What I come down to is how would early life manage to get hold of ribose as it expands and evolves so quickly? I mean, I think that to me, is this out? On what? Okay. So the Powner paper, I think it doesn't take account of the complexity that life requires right at its beginning. So it's effectively, you've got to have a metabolism that's going. It's got to be the engine that's going. And to make that analogy again, the computer is kind of helping to drive that metabolism. But the computer is something that is generated by that metabolism. So I don't think it's something that is found, for example, on the ocean floor or on the ocean surface. The ocean surface, I imagine at that time, you had extraordinary high tides, very, very large waves, no confidence to stop those waves. So it was not a peaceful ocean surface that people like Powner suggested. And I think Powner should do some geology and get a sense of what the early Earth's like. And I think, to me, the initial conditions are such that, I mean, Powner will say quietly that he doesn't care about the origin of life. It's just doing that work.
Just chemistry.
Getting that funding. And seems quite oblivious, or not careless, of the significance of his papers to the emergence of life. They look attractive to anybody who's not thinking too much. But if you think about how you would actually get ribose, I mean, there's lots of other ways of getting ribose. And of course, we're looking at what evolution has finally given us as ribose. Maybe we didn't start with ribose. Probably not.
Do you think that at least part of this UV-induced photochemistry might be relevant to help life along in the engine you're talking about?
You wouldn't want to be on the surface of the planet at that time for lots of other reasons which you've just pointed out. But one of them is just the wildness of that planet. We know we need free energy to get something going, but we don't need too much. So, and to me, that energy at the surface was just so wild in many different ways.
Might not there be some dialogue between the chemistry and the surface with the hydrothermal gas?
Sorry.
No dialogue.
No, I mean, one of us is going to be wrong. And it's going to be one of us. But you can't, science is not about compromise. It's about, as I say, it's about the fact that some things are just dead wrong, and many things are dead wrong, and only some things are going to survive, very clearly. It's the law of natural rejection, as I keep on saying. I want to get into more work about this, but the problem about that is something called the Simons Foundation. Are we on, how far are we? Are we broadcasting around the world? Or not?
We are in the web, so in the web.
Well,
Even China.
well, I think it's fair to say that Jack Shostak was telling us from around 2008 that another 5 years and we'll have a cell. And then in 2008 and 2012, it's another 3 or 4 years till we have a cell. And so all the Shostak people who all believe in the RNA world we're all waiting for their cells, but their cell has never transpired. Now, of course, it could transpire in the future, but it seems to me peculiar that they say, just give us 5 years. Well, we've given them 5 years. Then they've given them another 5 years. And nothing much has happened with the RNA world because basically the world works through proteins. It works through the active center of proteins. It works through changes of conformation of proteins. And the RNA world, of course, some kind of RNA control came in. But it's, to make that analogy with the hunter-gatherer society, you didn't have bureaucrats, you didn't have anybody telling you what to do with hunter-gatherer society. You had nothing telling you what to do right at the emergence of life. It's just something that can't help it because of this equilibrium. Most of this equilibrium for his world is against the growth of ribose. So it's him or us, really. And we'll find out. I'll be dead by then, but
We'll know eventually.
yeah, we'll know. Oh, we'll know eventually. Oh, we're definitely getting it. I mean, we can make stuff in the lab that makes sense. We can make, I mean, what can we do in the lab? Okay, people always say we don't do any experiments. I mean, that's their charge against me. We don't do any experiments. I'm a geologist. You know, Darwin didn't do any experiments. He saw the experiments in front of his eyes. He was smart enough to see what those meant. And he came around South America and realized that volcanoes deliver carbon dioxide. So Darwin said the early Earth was carbon dioxide, not all these other cyanide and all this stuff. And to my mind, he was dead right, because he had a geological sense of things. So, so what can we do? So, you know, green rust is something that is actually can operate like an engine. It can operate like a pump. It's actually it was there. The banded iron formations, the gigantic amount of that was all green rust. You don't have to worry about whether it was green rust or not in the Earth. You have to worry about whether it was rivals. But you don't have to worry about green rust. And what can we do with green rust? We can just quickly just say a few things. So, sorry, people might have heard it yesterday, that you can take nitrate in water and reduce it to ammonia with green rust in 3 hours. Now, you need 2 enzymes to do that in life. Nitrate reductase and nitrite reductase. But green rust can do it just 8 electrons in 3 hours. Now, it's not exactly biological, and nobody's trying to do it faster. But that's pretty extraordinary. And we can take that ammonia, and we can interact that ammonia with pyruvate and make alanine. And we can make it in quite a hard, 20% yields, large yields, not these kind of 0.2% yields, but large yields. And there's many people we've heard in other lectures saying how it's possible to make peptides from these, from very simple amino acids. Now, very particular amino acids, and I can tell you that we can take 3 or 4 peptide and we can wrap up cobalt and nickel and so forth, or if we take 7 peptides, it doesn't matter about the side chain at all, that doesn't matter, so you don't need coding for that. It's just because it's the backbone that actually takes in the cobalt, it takes in the phosphate, takes in the iron sulfides, and to this day, the P loop is exactly that structure. It's just a peptide. It doesn't have any, it's got a glycine in it, because it has this universal join. So we can actually get, I would say, to get into phosphate, we can make the P loop in the lab. Now, that doesn't sound like much to people who work in the RNA world, but to me, it's extraordinary, because every single ATPase and pyrophosphatase uses the P loop. And you can do it in the lab without life. So we would say we are doing experiments, but we're starting on the ground floor. Okay, there's a penthouse up there, and it's Harvard. And in that penthouse, that's hanging from the universal tree. But actually, you can't build a penthouse if you haven't built the structure beneath it. So we want to build the structure beneath it. So it doesn't sound like much, but we think we can take a step at a time.
There's actually a figure of speech from Jim Isaiah. He once told the audience in a meeting that some unraveling of the real mechanism from the emergence of life are going to be found reaction by reaction, a kind of battle of Stalingrad, house by house, reaction by reaction. Kind of agrees with what
Can I just say one thing about that? May I just quickly? But don't forget that life is not chemistry. Chemistry goes downhill thermodynamically. Life doesn't. Life goes uphill. It's hard work. It's extraordinarily surprising, life. Chemists have got nowhere doing life. It's because life uses engines. As soon as you look at an enzyme, you realize it's an engine. So we've got to have something like an engine right at the emergence of life, I would say. It's not chemistry. Or not just chemistry.
So anybody else? So let's thank Professor Gustavo once again. Okay. Now, our second lecturer in this afternoon, we have Alice Bosco. She's a BSc in biology by Federal Fluminense University and PhD in geology and natural research by State Campinas University. Now she works as a postdoc research advised by Professor Elson Oliveira in State University of Campinas. She worked with elemental traces in the estuary environment, application of unstable and stable isotopes in biogeochemistry, and geobiology of Earth and its analysis. Please, Alice.
I think now it's a trend to stay here, so I'm going to stay here too. So probably my talk will be a little different than the other ones because I'm actually showing my data for you and most of my important observations during my postdoc project. And I have been working at the same time with arcane terrains and also with model plates that are analogous of recombinant systems. And I will start saying that my major important tools are the stable isotopes. So I choose a few observations that I made based on stable isotopes to show you today. And, okay, so before I actually talk about data, I will come back to a point that I talked before, that is how it's important to improve methodology in geobiology sciences. And why I'm talking about that? Well, I'm looking for chemical signatures that were put in place by microorganisms. So imagine you that I'm going to the field, most of you should be geologists. We go to the field, we sample a rock like this big, we crush it, we prepare it, we analyze it, and we reduce it to one single number. And this one single number represents like a mix of process and a mix of microbial communities, and we have to make an interpretation using this one single number. So everything I can do to improve how I search for design and the precision of design, I will do, right? So this machine here, and no, Sharon was not paying me to do advertise about this machine, but I want to talk a little bit about that. I will be very brief. So this is an elemental analyzer coupled to a normal mass spec. And what this elemental analyzer do, it's the ISOLink. And the ISOLink allows us to change the temperature of the GC oven inside the elemental analyzer. So allow us to have like really good chromatography, put our efforts in one peak shape. And we have incredible peak shapes, what it means that actually we have incredible isotope data. And this machine also allows us to use smaller and smaller samples to analyze stable isotopes. So what is the important thing about that? If we use smaller samples, we have a better resolution on the stratigraphic column. As smaller sample we can use, higher resolution I can have, right? So this methodology has a high precision for carbon, nitrogen, sulfur, and no combustion additives are needed. You guys can see like the really sharp peak of sulfide analyzer here, so it's a very good pick. And what is really amazing, in one single sample, give us like data for nitrogen, carbon, and sulfur isotopes at the same time. So after I said that, and of course I use this methodology for what I'm going to show you, I think I can say that all my research is guided by the Great Oxidation Event, right? And inside this big and important event, I have like two major implications that actually explain why I'm working with a rock record at the same time I'm working with water lakes. Okay, so the first implication is, well, the oxygen was driven by oxygen photosynthesis. And this oxygen produced by oxygen photosynthesis that drove the Great Oxidation Event is actually credited for the expansion of multicellular eukaryotes. So understand the timing of the tempo, the Great Oxidation Event, is actually understand big steps of life evolution, right? And the second major implication of the Great Oxidation Event is like it happened at 2.4 billion years ago. So life was here before that. So life was anaerobic, right? So how much we know about this anaerobic life? So to understand a little better of the ecology of a specific group of anaerobic bacteria, an oxygenic photosynthesis sulfur bacteria, I have been working with moderate euxinic lakes. They are non-oxic lakes, analogous from before the Great Oxidation Event, and part of the water column has free sulfide dissolved. Okay, so first let's talk about the timing and the tempo of the Great Taxation event. And here, I think we have like so many proxies, right, to understand and to what's the word? It's a consensus between the scientific community, right? That the New Yorkian sequences probably have all the clues about this event. All the proxies are there and everything is there. One of the most important proxies is it's how the okay, so this graphic and the right. So how in the geological record, simply we have a sulfur mass independent fractionation of sulfur with some anomalous values of sulfur 33 disappeared on the geological record around 2.4 where we expected the GOE happen, right? However, I think we have a huge bias to understand not just the GOE, but also the sulfur mass record. And I'm going to say why. Here, this graphic on the right, at the downside, it's a big compilation of sulfur myth data from the geological record. And you guys can see that it's very easy to see that almost all data come from South Africa or Western Australia cratons. However, many paleogeographic fits have been showing that the two cratons from South Africa and Western Australia, the Kappa and Pilbara, were part of the same continuous basin at the time of the Great Oxidation event. So maybe everything that we know about a super important global process has actually all the data from local response, right? So I have been trying to open people's mind about that, just because here in Brazil we have such important craton. Actually, we have two, but we have this such important craton, the San Francisco craton, that has like amazing sequence for 2.7, 2.6, 2.5, 2.4 billion years, explaining all the GOE. Okay, so I have been working with several drill cores from the New Yorkian of San Francisco craton. San Francisco craton is an expansion of the West Coast craton in Africa. And here I'm going to show data for you for one of these drill cores. This is the drill core NL1. This drill core, it corresponds to the Noveling group, what is part of the Rio das Velhas Limestone Belt. Probably everybody who's from Brazil heard about it, and the Vale do Ferrito in the central Brazil. And in the literature, this is a very well-studied greenstone belt, but not at the geobiology approach, just like normal geology stuff. So in this sequence, it's dated from 2.7, 2.715, and here this core, I dated part of it. So this core is composed by chert, iron formation, graphite schist, and carbonate chloride schist. The metamorphism is green schist. So using running lab dating zircons by LA Isabemas, I dated this sequence with a minimum weight of 2.76. Okay? So let's see a little bit about the data of this core. So this is part of my multi-proxy approach. Of course, when I started this project, no one believed in anything that I was saying, right? It's a very different approach for like a geology in Brazil. So I decided to use as much as data that I could use. I used like many proxies together. And using these many proxies together, I could observe through this sequence changes in redox conditions, but also in ecological conditions. And I divided them in three phases. So the phase 1 is the green, the phase 2 is the orange, and the phase 3 is the blue. And of course, I don't have time to show you all my data and go to all the interpretations, but I'm going to show like a piece of the cake here. So what I can see from many proxies, and one of them is iron speciation, and I have an oxic deposition at phase 1 and 2, and go to an oxic deposition at phase 3. So these anoxic and noxic conditions are supported by many other proxies. And one of the proxies that are supported, phase 1 and 2, or deposited in anoxic conditions, is, for example, the absence of serum anomaly, negative serum anomaly, and the iron formations from phase 1. I'm sorry that I put the picture from the rock really, really small, but it's an amazing laminated bandar information. You can see like primary structures and everything. And so one difference that I see between phase 1 and 2 is that in phase 2 I have a bigger amount of pyrite on the rocks. And this amount of pyrite, sulfides, and also carbonates, and also their enrichment factor in molybdenum and a positive correlation of molybdenum with organic carbon allow me to interpret that probably the basin from this core was actually moving towards oxenic conditions from phase 1 to 2. And the sulfur isotopes behavior is completely like sulfur myth, or it means that the fractionation was formed by independent process, mass independent process in an oxic atmosphere, and followed the Archean ray from phase 1 and 2. So what was my surprise when I arrived at phase 3, I see the loss of sulfur myth. And actually, I have a sulfur MDF process forming the fractionation. I have much more data in that. One example is the sulfur 36 and many more, but anyways, this is what I have time to show you guys. However, we also understand that this oxygenation was not really big or complete. And one way that we can say that is if we look to the regular 34 fractionation, that is the graphic in the right. So at the bottom of the core, we have most of the pyrites, the sedimentary pyrites with crustal bubbles. And at the top of the core, we moved like to a heavier fractionation. And this can be interpreted like a sulfate limit basin. So we are limiting sulfate production, so we don't have like big fractionation. Which means that probably we have a record of oxygen oasis or like early oxygenation. We are almost like onset of oxidative wetting or something like that. So now that I talk a little bit about my rock data, I'm going to show you really brief my data about the anoxic lakes. And you will see very easy the correlation between one and another. So these lakes I have been working with, they are anoxic lakes because part of the water column just does not have oxygen dissolved. And we actually have hydrogen dissolved. So this is a picture from how the water column looks like, the photic zone. Okay, so this is a specific group of bacteria. They are photosynthetic, but they do not produce oxygen. They fix carbon dioxide, and they are called anoxygenic photosynthetic sulfur bacteria. This is why they oxidize hydrogen sulfide or iron 2. And they are from two principal groups. One group is the purple sulfur bacteria. It classically is expected to oxidize hydrogen sulfide. The second group is the green sulfur bacteria that is expected to oxidize hydrogen sulfide or iron 2. So for many, many years, organic geochemists and geologists have been focused about this bacteria for a specific aspect. When they look at these modern lakes, they realize that the purple sulfur bacteria requires much more light to produce photosynthesis, and they tolerate more oxygen than the green sulfur bacteria. So 10 years ago, when what Nara talked about a little bit before, when the biomarkers from this bacteria started to be found in the geological record, and I agree with you, it's kind of impossible to say they are syngenic, but anyways, people started to find the biomarkers of this bacteria, and they just start to make implications about environmental reconstructions. When they found biomarkers of purple sulfur bacteria, they were saying that the environment was shallow, and also they were saying that it have necessarily oxenic conditions, because this bacteria classically was supposed to just oxidize hydrogen sulfide. So let's look the data from one of the lakes I have been working with. This is Light Blue Lake in Washington State. And this is a very shallow lake at 60 meters deep. And at 10 meters deep on the climacline, when all the oxygen is consumed, and we have started to see like hydrogen sulfide free in the water column, and almost all the light is consumed too, we see purple and green sulfur bacteria living together. So this was really surprising, because the model that has been applied to the geological record to interpret these biomarkers, it's not working in a really shallow lake like light blue. And another thing that we looked for at this lake was the offset between the fractionation of sulfur-34 between sulfate and sulfide. This isotopic offset has been used to interpret in the ancient geological record the sulfate, the amount, the size of the sulfate pool. So as much more sulfate you have, much more fractionation you're supposed to have. However, you can see like in this graphic at right, I put like an arrow here. Here you see light blue. So light blue has a really small sulfate pool in relation to the gray points. Whether it's 22 is another lake that I work with, this Mahoney Lake that has like a really big sulfate pool, like 500 millimoles. And light blue lake has a sulfate pool of about 10 millimoles. And the fractionation between these two lakes are the same, right? It's around 50 per mil. So what is the implication of that? The implication, if you think about oxygen, the ocean evolution, is that at the levels of sulfate pool of light blue, close to 10 millimoles, this is not more unreliable to interpret the sulfate pool in the ocean. So one interesting thing is that we went to look like a little bit about the redox history of this lake. And this is why we looked for it. PSB, purple and green sulfur bacteria living together, are really weird. It's really weird. But then when I looked like deeper on it, we saw the green sulfur bacteria that live on this lake just not oxidize just sulfide, but also oxidize iron too. So my first thought was maybe they were there because the lake, before being eosinic, was a ferruginous lake. And when I looked at the history of the redox of this lake, I actually saw that for most of the time, the lake was an oxic lake. And just close to the small ice age, I think this is the translation, okay, the small ice age, the lake actually turns like ferruginous, anoxic. And before it becomes free in hydrogen sulfide in the water column, we could see signs that we had like iron 2 dissolved in the water column. And all this time, since the lake becomes anoxic, we could observe purple and green sulfur bacteria living together. So this is represented here by the 15 centimeters deep. So I'm going to just summarize my observations. So about the rocks, I really believe I have evidence of substantial rise of oxygen at 2.76 billion years ago, indicated by the sharp decline of sulfur myth and in the core NL1. And I really believe that the oxygenation of San Francisco Craton is a new piece in the GOE puzzle. I have many cores, I analyzed many sequences, and no one knows about that. So we need to do work on it right now. Please, Nora, come here, let's do that. And also, the sequence record a localized transition in water called redox. And this transition is happening 200 billion years before the Great Oxidation event, and much before all the transitions observed in the Capaval and the Pilbara Craton. Okay, so the same kinds of water column redox transitions we observed here a few million years before. We have like one of the oldest records of eoxenia, what implies an oxygenic photosynthesizers as the present producers. And about the lakes, I have to say that we did not observe resonation between green and purple sulfur bacteria and the photoxone, right? So what this means that if you find remains of these bacteria in the geological record, this is not reliable to interpret shallow water chemoclides. As well, it's not good to interpret water column eoxenia, since we're seeing with clarity that PSB, purple sulfur bacteria, can also live in ferruginous conditions. And to finalize, the sulfur isotope signatures in sulfide and sulfate and sulfide in the geological record have a limit utility estimated under seawater sulfate already at the levels of sulfate of lime blue. So already at the levels at 10 millimoles, I really think this is not a good tool to estimate the seawater flow. Okay, so obviously the fractionation on this lake was not affected by the size of sulfate reservoir. And with this, I want to thank you guys, and also I really want to thank Flavio for inviting me. It was a really nice opportunity. Thank you.
So thank you, Alice, again. So, does anybody have any questions for her? Nobody?
No questions?
No questions?
Nothing? Absolutely nothing?
So let's thank Alice again. Is that a question?
No, I just said the acronyms.
No, thank you. But I'm going to show like a piece of the cake here. So what I can see from many processes, and one of them is iron association, and I have an oxic deposition at phase 1 and 2, and goes to an oxic deposition at phase 3. So these anoxic and oxic conditions are supported by many other processes. And one of the processes that are supported, phase 1 and 2, or deposited in anoxic conditions, is that, for example, the absence of serum anomaly, negative serum anomaly, and the iron formations from phase 1. I'm sorry that I put the picture from the rock really, really small, but it's an amazing laminated bond iron formation. You can see like primary structures and everything. And so one difference that I see between phase 1 and 2 is that in phase 2 I have a bigger amount of pyrite on the rocks. And this amount of pyrite, sulfides, and also carbonates, and also their enrichment factor in molybdenum and a positive correlation of molybdenum with organic carbon allow me to interpret that probably the basin from this core was actually moving towards oxenic conditions from phase 1 to 2. And the sulfur isotope's behavior is completely like sulfur myth, or it means that the fractionation was formed by independent process, mass-independent process in an oxic atmosphere, and followed the Archean ray from phase 1 and 2. So what was my surprise when I arrived at phase 3, I see the loss of sulfur myth. And actually, I have a sulfur MDF process forming the fractionation. I have much more data in that. One example is the sulfur 36 and many more, but anyways, this is what I have time to show you guys. However, we also understand that this oxygenation was not really big or complete. And one way that we can say that is that we look to the regular 34 fractionation, that is the graphic in the right. So at the bottom of the core, we have most of the pyrites, the sedimentary pyrites with crustal bubbles. And at the top of the core, we move like to a heavier fractionation. And this can be interpreted like a sulfate limit basin. So you're limiting sulfate production, so you don't have like big fractionation. Which means that probably we have a record of oxygen oasis or like early oxygenation, or like onset of oxidative weathering or something like that. So now that I talk a little bit about my rock data, I'm going to show really brief my data about the anoxic lakes. And you will see very easy the correlation between one and another. So these lakes I have been working with, they are anoxic lakes because part of the water column just does not have oxygen dissolved. And we actually have hydrogen dissolved. So this is a picture from how the water column looks like, the photic zone. Okay, so this is a specific group of bacteria They are photosynthetic, but they do not produce oxygen. They fix carbon dioxide, and they are called oxygenated photosynthetic sulfur bacteria. This is why they oxidize hydrogen sulfide or iron 2. And they are from two principal groups. One group is the purple sulfur bacteria. It classically is expected to oxidize hydrogen sulfide. And the second group is the green sulfur bacteria that is expected to oxidize hydrogen sulfide or iron 2. So for many, many years, organic geochemists and geologists have been focused about this bacteria for a specific aspect. When they look at these modern lakes, they realize that the purple sulfur bacteria requires much more light to produce photosynthesis, and they tolerate more oxygen than the green sulfur bacteria. So 10 years ago, when what Nara talked about a little bit before, when the biomarkers from this bacteria started to be found in the geological record, and I agree with you, it's kind of impossible to say they are synthetic, but anyways, people started to find the biomarkers of this bacteria, and they just start to make implications about environmental reconstructions. When they found biomarkers of purple sulfur bacteria, they were saying that the environment was shallow, and also they were saying that they have necessarily eugenic conditions, because this bacteria classically was supposed to just oxidize hydrogen sulfide. So let's look the data from one of the lakes I have been working with. This is Lime Blue Lake in Washington State. And this is a very shallow lake at 60 meters deep. And at 10 meters deep on the climacline, when all the oxygen is consumed, and we have started to see like hydrogen sulfide free in the water column, and almost all the light is consumed too, we see purple and green sulfur bacteria living together. So this was really surprising, because the model that has been applied to the geological record to interpret these biomarkers, it's not working in a really shallow lake like Lime Blue. And another thing that we looked for at this lake was the offset between the fractionation of sulfur 34 between sulfate and sulfide. This isotopic offset has been used to interpret in the ancient geological record the sulfate, the amount, the size of the sulfate pool. So as much more sulfate you have, much more fractionation is able to have. However, you can see like in this graphic at right, I put like an arrow here. Here you see lime blue. So lime blue has a really small sulfate pool in relation to the gray points. Whether it's 22 is another lake that I work with, this Mahoney Lake that has like a really big sulfate pool, like 500 millimoles. And Lime Blue Lake has a sulfate pool of about 10 millimoles. And the fractionation between these two lakes are the same, right? It's around 54 mil. So what is the implication of that? The implication, if you think about oxygen, the ocean evolution, is that at the levels of sulfate pool of Lime Blue, close to 10 millimoles, this is not more unreliable to interpret the sulfate pool and the ocean. So one interesting thing is that we went to look like a little bit about the redox history of this lake, and this is why we looked for it. PSV, purple and green sulfur bacteria living together, are really weird. It's really weird. But then when I looked like deeper on it, we saw the green sulfur bacteria that live on this lake just not oxidize just sulfide, but also oxidize iron 2. So my first thought was maybe they were there because the lake, before being eosinic, was a ferruginous lake. And when I look at the history of the redox of this lake, I actually saw that for most of the time, the lake was an oxic lake. And just close to the small ice age, I think this is the translation, okay, the small ice age, the lake actually turns like ferruginous, anoxic. And before it becomes free in hydrogen sulfide in the water column, we could see signs that we had like iron 2 dissolved in the water column. And all this time, since the lake became anoxic, we could observe purple and green sulfur bacteria living together. So this is represented here by the 15 centimeters deep. So I'm going to just summarize my observations. So about the rocks, I really believe I have evidence of substantial rise of oxygen at 2.76 billion years ago, indicated by the sharp decline of sulfur myth in the core NL1. And I really believe that the oxygenation of San Francisco Craton is a new piece in the GOE puzzle. I have many cores, I analyzed many sequences, and no one knows about that. So we need to do work on it right now. Please, Nora, come here, let's do that. And also, the secret record a localized transition in water called redox. And this transition is happening 200 billion years before the Great Oxidation event, and much before all the transitions observed in the Kappa and the Pilbara Craton. Okay, so the same kinds of water column redox transitions we observed here a few million years before. We have like one of the oldest records of dioxin, what implies an oxygen photosynthesizers as the primary producers. And about the lakes, I have to say that we did not observe resonation between green and purple sulfur bacteria and the photoxone, right? So what this means that if you find remains of these bacteria in the geological record, this is not reliable to interpret shallow water chemoklides. As well, it's not good to interpret water column dioxin, since we're seeing with clarity that PSB, purple sulfur bacteria, can also live in ferruginous conditions. And to finalize, the sulfur signatures in natural sulfide and sulfate and sulfide in the geological record have a limit utility estimated under seawater sulfate already at the levels of sulfate of lime blue. So already at the levels at 10 millimoles, I really think this is not a good tool to estimate the seawater flow. Okay, so obviously the fractionation on this lake was not affected by the size of sulfate reservoir. And with this, I want to thank you guys, and also I really want to thank Flavio for inviting me. It was a really nice opportunity. Thank you.
So thank you, Alice, again. So, is anybody have any questions for her? Nobody? No questions?
Nothing? Absolutely nothing?
So let's thank you, Alice, again. So, is that a question?
No, she said the acronyms.
No, thank you.
So let's thank Alice again, please. Okay, our last but not least lecturer here is to Dr. Douglas Galante. Douglas Galante is BSc in Molecular Science by the University of São Paulo, PhD in Astronomy by the same university, and now he's currently working in Brazilian Synchrotron Laboratory. He's associated also to USB Research Unit in astrobiology, and he's working now in astrobiology and planetary science besides his works on origins of life. Basically, he's working in life-environment interaction and its extrapolation to outside of terrestrial context. Also, he's working in the emergence of life and habitability in solar system, and he is a guarantee of the Serra Figueira Institute here in Brazil. Douglas, to you.
Thank you very much, Thiago, for the flattering introduction. Well, most of the time I try to kill life instead of creating life, but anyway, let's go on. What I'm going to talk about is a bit about the Synchrotron Laboratory, because we're going to make a visit tomorrow. The idea is to give you a general introduction of what synchrotron is, what we can do, and maybe give some hints on what we can do to study ancient life on Earth, fossils, and maybe some origin of life related studies, such as with some minerals. So that's something that we have been doing. So the Brazilian synchrotron light laboratory is based is essentially an X-ray source. So it's a radiation source. Normally we say it's a synchrotron light source. And X-rays are very interesting. They are, as you know, discovered by Röntgen in the 1800s. And they are interested. They caught a lot of attention because of their property of being transmitted by matter and seemingly invisible. So they were promptly applied. As you know, all men are very brave, and so was Röntgen. So he took his wife's hand and put in front of this unknown radiation to see what happens. Of course, it was very brave. And this is his wife's hand. We can see the wedding ring. And so we could see inside the hand without having to cut it open. This was applied for medicine, and it was a huge revolution, as you all know, as you all we can do. But of course, we can apply it for a variety of different studies, and the interaction of radiation with matter can be explored for different types, with different types of fields. And that's what I want to show. And synchrotron are very generous and flexible X-ray sources, or photon sources, in fact. And to connect with this session in which we are trying to discuss biosignatures and habitability of the universe with the cosmos, I wanted to say that synchrotron radiation is not something that is just produced on synchrotron laboratories, of course, but it's a general property of radiation of charged particles inside already a magnetic field, and this is available in the universe in a plethora of places, such as these giant jets that produce this light by synchrotron radiation. So these are essentially electrons that are spiraling around the high magnetic fields that is present in these astrophysical sources. So synchrotron radiation is a source of light, of X-rays and light in different energy ranges on our universe. It's a non-thermal source of radiation. And of course, you all know neutron stars and pulsars, which are these objects, these very compact objects with high magnetic fields. They also produce a lot of synchrotron radiation that we can detect as pulsars. And you may know pulsars were used to detect the first exoplanets ever, so they're very important. Well, but why do we need synchrotron radiation? Because you all know that we can produce synchrotron light using X-ray tubes, and these can be very small, they can be very compact. Nowadays, you can buy something that is the size of a cell phone. It can even be battery powered, so it's portable. So why do we need synchrotrons? Well, on an X-ray tube, you produce radiation by Bremsstrahlung, by deaccelerating the electrons in a metal, and this will produce the radiation itself. But when we're talking about synchrotrons, what we do is we make the electrons go around a path by applying a magnetic field to force them to make the curves. And when they make the curves, they will produce the radiation. This is the general law that we see here. If you take Maxwell equations, we see that every time that you have, almost every time, that you have an acceleration, you're gonna, accelerating charged particle, you're gonna have the production of electromagnetic radiation. So that's what we do with the synchrotrons, and this can be very large machines, kilometer-sized machines. For those going to the synchrotron tomorrow, you're going to see that this is a really big machine. This is the Diamond synchrotron on the UK, near Oxford. So this is very big. So why do we need something that is a kilometer-sized machine instead of something that is 10 centimeter size? There has to be some advantages, and there are a lot of advantages in going to the synchrotron machine. Inside the synchrotron machine, what we have is essentially this. We have what we call the storage ring, which is a large machine. It's essentially a large vacuum pipe, which can be around 1 kilometer in circumference. And in these pipes circulate the electrons, and inside these pipes or around them, we place electromagnets of different types. They can be dipoles or multipoles, depending on what we want. And this is going to force the magnetic particles to turn around, to make curves, to undulate, or to wiggle around. And every time they do this, they're going to produce photons. And these photons are then collected and transmitted through a series of optics, monochromators, mirrors, slits, whatever, to make the radiation red to probe our sample, to make it small, to make it coherent, to choose its energy, so that we can extract the information that we need. So this is essentially what a synchrotron is. And the beauty of this is that we can, I'm going to stand here to point. The beauty of this is that we can apply a variety of techniques once we have this radiation. So essentially the radiation is one thing. We can tune the energy, as I was saying, and we can explore different physical phenomena. So we can have diffraction, we can have absorption, we can have scattering, so we can have different types of matter-radiation interaction that we can explore to extract information of the elemental composition, the oxidation states, the chemical neighborhood, or the local organization of the systems. And we can do this, essentially we can do this, we can collect this data very fast so we can have temporal resolution, so we can do in situ and in operando studies. And this is very important when we talk about the kinetics of a reaction in prebiotics, in a prebiotic reactor or something like that. So that's something that we can do. So the idea is that we can explore different types of physical phenomena to extract the information that we need from our sample. And this is a comparison of the emission spectra of synchrotrons with an X-ray tube. So here we have the emission spectra of an X-ray tube. Essentially, we have a very narrow line, which is the emission line of the metal that the tube is made of. This is a copper X-ray tube, and this is the intensity of the radiation that is being produced. So we see that the X-ray tube produces monochromatic radiation and of very low intensity. When we go to synchrotrons, and this is what we call a second generation synchrotron, which is the same that we are going to visit tomorrow. It's an old synchrotron, the UVX, the machine that we are turning off at the moment. We already gain about 1 million times influx in radiation brightness when you go to this type of synchrotron in comparison to the X-ray tubes. And in addition to this, we gain in energy range. We don't have only monochromatic, but we can go from the infrared to the hard X-ray regime, and we can tune the energy to the experiment that we need. At the moment, the current generation of the synchrotrons is the third generation, which is such as Diamond on the UK, Soleil or SRF in France, or APS on the US, or on many other places. So this is the third generation machines. We have the new, which this has about 1 million times more flux than the second generation. We are going now to the fourth generation, which is the synchrotron that we are going to visit tomorrow. In fact, Sirius, the new synchrotron we are building, will be the second, fourth generation machines in the world. So it's a very important technical achievement that we're doing here in Brazil. So these are the main advantages. We get a lot of flux. I think I have here. We have a lot of flux, much more than an X-ray tube. We have a broad energy range, which allows me to probe different types of physical phenomena. We can choose the energy, so we can be elementally specific. We can choose just the sulfur, just the iron, just the potassium, or whatever, almost all elements on the periodic table, and we can do spectroscopy, or we can do mapping, or we can do imaging of these types of these different elements on the sample. The source can be very focused, so we can have very small sources, very small probes. This allows us to map and to study heterogeneous materials, which is essential when we go to rocks, to geology, or to fossils. And now, synchrotron sources have high coherence, which means that the source is essentially like a laser. All photons are in phase, and this allows us to explore different types of diffraction based on coherent light. And this allows us to go deep in resolution. That's something that I'm going to show. I have one result of coherent measurement here. So with this, we have high spectral resolution, high spatial resolution. We can be elementary specific, and we can apply multiple techniques. These are our good qualities of synchrotron light. The bad things, it demands a lot of training, so it's not something that is just push and go, but it demands training. It's expensive, so it's not so easy to get time at the synchrotron. I'm going to talk about it. It's free, but it's of course the government is paying for you. So it's very competitive. Of course, it's not portable. We're not taking a synchrotron to Mars for now. And it's meant for more specific and complex problems, such as in situ inoperando studies. Well, the Brazilian Synchrotron Light Laboratory. This is the picture of the current machine that we have, UVX. It was opened for users in 1997 as the first synchrotron on the southern hemisphere. Just in 2005, Australia opened one, but we are still the only one in Latin America, so we have a lot of local importance here. We have about 30 internal researchers. We receive about 1,500 external researchers per year. They are all academic, mostly they are all academic users paid by our government to do these studies, so we don't charge anything for that. Instead of this, we have our own funding program to allow that anyone in Brazil can use our facilities cost-free. So if someone from Manaus, from Amazonia, gets some beam time, our lab pays for everything, for all the expenses, so that the people can come and do their experiment for free. Of course, we have a lot of postdoc students in the year, and the mission is to be an open user facility for the whole Brazilian and international communities to do the best of synchrotron light can do. The LNLS, which is the Brazilian Synchrotron Light Laboratory, is inside a bigger campus called CNPEM, Centro Nacional de Pesquisa em Energia e Materiais, in Campinas, just behind Unicamp, but we are linked to the Ministry of Science and Technology. And inside CNPEM we have 4 national labs. We have the Synchrotron Lab, we have LN Nano, the Nanotech Lab, we have LN Bio, the Biosciences Lab, and we have LNBR, the Biorenewables and Biorenewables and Biofuels Lab. So we have 4 national labs working in synergy to tackle very different and multidisciplinary challenges nowadays. And of course, Origin 5 is one of them. We are there. At UVX, we have, at the moment, still operating 18 beam lines going from the infrared to the X-rays. And tomorrow we're going to have the chance to see some of these beam lines. They will be working. We have beam tomorrow. There we do spectroscopy, scattering, small angle scattering, diffraction, and imaging of different types, 2D and 3D, of very high resolution. And we're going to discuss this more tomorrow. So we have different types of techniques that we use. Just some slides on some of the techniques. When we talk about diffraction, and most of you know diffraction, but essentially what we do with diffraction, we pass light through an organizing material, normally a crystal of some kind. It can be an organic or inorganic crystal. This will scatter lights in a very specific way, in a way that reflects the charge density of your material. And with this, you can reconstruct the 3D, in a sense, structure of your atoms inside your sample. And this was used in 1953. You all know this picture, probably. This is the X-ray diffraction pattern of a DNA crystal by Watson Crick, or most people will say from Rosalind Franklin. Let's be honest. They used her data. And this was used to show that the DNA has the double helix structure. So when you see a molecule like that, a structure like that, you should know that most of the times this macromolecular structure was defined at synchrotron. So we do a lot of crystallography, a lot of 3D structures at the synchrotron lab. But nowadays we can do this even in with micro resolution. That's something that is completely impossible to be done at the lab sources normally. This is an example of a meteorite that was mapped in 2D by X-ray diffraction, so you can do mineralogy. You can do the mapping of the different phases with XRD. That's something that can be done at synchrotrons. And this is another example of, I don't remember what was the reaction, but essentially what we're seeing here are some diffraction peaks that is appearing as you change the temperature. In fact, it's disappearing as you increase the temperature, probably because you're getting it more disordered. What you can do this in situ in operandi studies to see how your material behaves with temperature, with pressure. You can simulate deep earth environments. For instance, we have a group at our lab that studies extreme environments, high pressures and high temperatures, gigapascal, so mental pressures, and how minerals are formed in this condition. Perovskites can be studied in this way, in situ in operandi, their formation and change. And nowadays, a lot of effort is being put to develop imaging techniques, especially in 3D. That's something that can be done at synchronous. And you're going to see tomorrow as well a micro CT beamline. So it's a tomography beamline, computed tomography beamline. With this, what we do is we collect images of your sample in different angles, and then we do a mathematical transformation to retrieve the 3D structure of your material with very high resolution. In comparison to a normal CT scanner, we have a resolution which is about 1,000 times greater than the normal CT scanner. So it's much, much better. And nowadays we're going to even better resolutions. And with this we can map, this is just a map of a bone, and we can see the vases and the structures inside of the bone with submicron resolution. So that's something that can only be done at synchronous nowadays. And this is a Brazilian example that my group has been studying for quite some time. This fossil comes from the Araripe region, from Ceará, the north of Brazil, which is a conservat lagerstätten. I hope I said it right. Which is a place of exceptional preservation of fossils. And this is a fish that was discovered there, very well preserved. It is so well preserved that we could image using synchrotron X-rays, coherent synchrotron X-rays, and with this we could find inside the fish the organs of the fish, and most importantly we could find the heart. It's not, you can't see very well, but the heart here is in red, and we could even see the valves of the heart, and we could study the evolution of the valves of the heart with time and compare with modern fish and see how they behave with time. And this has about 110 million years old. So they were here around with the dinosaurs at the moment. And we could do this. But we could also map with XRF, with X-ray fluorescence, the elements on this valve, on the heart. So we could see how the elements were distributed in them. We have done also spectroscopy to see the oxidation state of the iron and the zinc inside the material. So we can do this. We could do all this with the synchrotron sources. So it's something that's very interesting. We could apply a lot of different techniques to study these ancient fish. Oh, and that's a video that I wanted to show, but it's not working here. Oh. So what is next in terms of 3D imaging is something like this. This is a pillar of a rock of 15 microns in diameter, so it's very small. It comes from the Gunflint Formation in Canada, Minky Mountain. It has about 1.8 billion years old. It's very old. And I think you remember Evan's talk. She showed some of the Gunflint biota, the fossils there. And this is what we discovered inside these rocks. We found these filaments inside the rock, which were already described as being fossils, but we could do more than that. We could map the electron density and the mass density of the materials, so we could identify the phases of the iron oxides that we had there, the carbon that was preserved in terms of kerogen, and the voids inside of it, and we could start discussing. And with this, we could discuss a bit more on the mechanism of preservation of these very ancient fossils. And these images here represent the forefront of the application of nanotomography. The resolution that we could get here is 50 nanometers. It's sub-micrometer, it's subcellular. We could in principle even see organelles if they were in there. So it's a technique to be used for the samples that come from Mars, for instance. something that we can do. So this all can be done in synchronous. And this is just for fun, because I like opera, and we have Nora here, which is a fantastic opera singer, as I heard. And this is an example of an opera written by Cherubini. And Cherubini was very dissatisfied of what he has written, and he erased part of the opera using some ink, but he used a carbon-based ink to erase it. And on the back, he had written it with an iron-based ink. So what we have done, we have mapped the iron behind the carbon using synchron light, using XRF. And with this, we could read what was behind the carbon-based ink. And in fact, the opera was reconstructed and played in 2012 in full for his demise, I guess. But that's something that we can do. We can see the invisible, in a sense, of ancient samples. Well, just to go into an end, I would like to talk a bit about Sirius. Sirius is the biggest science project that we have nowadays in Brazil. It's costing a lot of money. We are working on this machine. We started building it in 2014. We are coming to a conclusion now. It's going to be ready by this year, hopefully. And the synchrotron machine is a new synchrotron. It's a higher energy synchrotron. It's a 3 GeV machine. Giga-electron-volt is just a unit, which means that we can extract very hard X-rays, X-rays of very high energy from this machine. It has a very low emittance, which means that we can focus the beam into very small spots, and we can use this to do very high resolution studies of materials, of heterogeneous materials. We can cover energies going up to 150 kilo electron volts, which is higher than the X-ray machines that you have on the hospital, for instance. So you can penetrate matter of the size of a body. So you can, in principle, do full body tomographies with very high resolution. That's something that can be done at the synchrotron machine. It's quite big. It has a 520 meters circumference. It will be able to accommodate 39 beam lines, which are the experimental stations where you do the experiments. So a lot more than today. Today we have space for 18. It's costing about 1.3 billion reais that is being paid by the Ministry of Science. And it's a fantastic opportunity for challenging new fields. And that's what I want you to excite to use it. It has an international importance because for the moment, Sirius and Max 4 in Sweden are the only 4th generation machines that are coming online. So we are at the forefront of the application of synchrotron light in the world. Other machines are being upgraded on the US and on France to also be 4th generation machines, but it will take some years for them to come online. So we are on the front of that. And this is what I was talking about, the emittance. Sirius is at the moment the lowest emittance machine, which means the best focused X-ray beams and the highest flux, the highest brilliance of X-rays on the world. So we are competing with Max 4 in Sweden, but hopefully we're going to win this battle for at least for the first years. And this can be done by a very smart design of the machine. The design was made here in Brazil. And so about 85% of the whole machine is being built in Brazil. The whole design is Brazilian. The whole machine is being built by Brazilian companies. And the magnetic design, so to turn around the electrons, we need a lot of magnets. We need dipoles. Each corner of the machine has 5 dipoles. And we have 120 dipoles in total to turn around the whole machine. So we have a lot of magnets to turn it around and to make sure that the electron beam is kept focused and very well collimated and behaves very well so that we can produce the X-ray photons. This is all done in Brazil. The vacuum system is very special. In fact, we have made a collaboration with CERN in Switzerland to use a technique that they developed there for the LHC, the Large Hadron Collider. So we are using the same technique called negative coating to produce the high vacuum that we need inside of our machine, because our pipes are very small. They are just 80 millimeters across. They're very small. It's a very small tube, and we need to pump it. And this can only be done by this nag coating. All the electronics for the control is made here in Brazil as well, and the design of the building was something that was achieved here on our country. In fact, the floor was developed in Campinas, and it was developed to be the most stable floor for sure here in Brazil. It has a lot of stakes that are directly linked to our block below the system. Then we have 4 meters of cement with soil mixed, and then 90 centimeters of a concrete slab that turns around the 500 meters in circumference to make sure that we have this nanometer stability that we need to make the measurements of very small beings. The whole building is aerodynamic. We have to control the temperature in 0.5 degrees Celsius inside of it, 0.1 degrees inside of the experimental stations. So we have a lot of stability that needed to be done and developed there. And the radiation sources, the dipoles and the wigglers and ondulators are also being developed here in Brazil. They have a new design that we are working together with APS, the synchrotron in the US. So we are working in collaboration with them to develop it. And with this, we plan this is a spectrum of what we plan to obtain with the dipoles and with the ondulators, which are these different sources. And we are planning to get a flux of very high intensity, much higher than Diamond and Soleil. Diamond is on the UK, Soleil is in France. So we're just comparing the fluxes that we plan to get on these machines, and Sirius will be the brightest X-ray source in the world, if everything goes fine. And not only that, we are planning to get a lot of coherent flux out of the machine, especially when we go to lower energies. Here at lower energies, we're essentially going to have an X-ray laser, and this is very important for coherent diffraction imaging techniques, such as the one that we use to get this nanometer scale resolution imaging of the fossils. And with this, the possibility of going to very high energy allows us to probe different types of elements. For instance, this is a comparison of the elements that we can achieve, that we can do spectroscopy at the UVX, which are marked here in green. Because of the limitations that we have nowadays in terms of energy, we can't cover all the elements, but with Sirius we have enough energy to go around all the elements on the periodic table. So it's a very flexible machine to study materials in general for different types of applications. And this is just a video to show you what's inside the accelerator. Let me see if it works. So this is a video showing the assembly of the accelerator, which is just being finished. We are in the phase of commissioning of all elements, all magnets, all the vacuum pipes, all the electronics. This is all ready nowadays, and we are entering the phase of commissioning. So if you're going tomorrow, unfortunately, we are not going to be able to enter the tunnel where the accelerator is. We're going to stay outside. And so, but with this, you can see what's inside there, all the elements that were assembled to make sure that the electrons go around smoothly. And I guess that's it. What I wanted to show you is that synchrotron machines are very flexible machines to study materials of different kinds, which can be rocks, which can be prebiotic minerals, which can be fossils, or could even be organic matter nowadays. From single-cell tomography, which is something that we are just developing, to whole-body tomography, which is something that will also be possible. Okay, so thank you very much.
Thank you, Douglas, for the amazing speech. Does anybody have any questions for Professor?
I think I have. Posso perguntar? Posso falar em português? Pode. Douglas, é que eu participei da visita aos Sirius quando falou com o equipe, você disse que... Como vai funcionar essa visita? Vai ser com esse grupo daqui?
A visita aqui, infelizmente a gente não conseguiu um ônibus para ir, então basicamente é por conta própria. A gente vai se encontrar lá no campus dos Sírios, do Síncrotron, às 10 horas da manhã. A gente vai ter uma visita de mais ou menos 2 horas, passando pelo acelerador atual, pelo VX e pelos Sírios.
Sim, só para saber, eu já pensei em fazer aquele programa de verão lá, mas a pergunta central que eu queria fazer quando a gente foi, você falou que estava sendo cortados os gastos em relação aos Sírios por conta do governo Bolsonaro, e queria saber como que anda esse...
Eu não posso falar do meu chefe.
Seu chefe?
Esse ano a gente teve um contingenciamento também nos Sírios, de mais ou menos 2/3 do orçamento que ficou congelado. Então a gente não tinha dinheiro para terminar o ano, basicamente, para honrar os nossos contratos de construção dos Sírios. A gente estava com a corda no pescoço, mas felizmente o dinheiro foi descontingenciado e a gente teve a verba suficiente para completar esse ano. Então, o que eu posso dizer a gente tem o dinheiro para completar 2019, para colocar os Sírios online, colocar as primeiras linhas de luz funcionando. O que a gente sabe é que ano que vem a gente vai ter que voltar à briga de novo. E é uma briga direta. Mas, por enquanto, a gente está com o dinheiro na mão.
E eu lembro também, você tinha falado algo sobre uma previsão de, por exemplo, teria um prazo de vida, tinha dito algo, por exemplo, em 2030, isso aqui já, acho que tem que ser renovado, né? Ele não perdia alguma das suas funções, ou talvez não seria o mais de ponta da...
É sempre uma briga tecnológica, né? Conforme a tecnologia avança, os aceleradores, essas grandes máquinas, elas avançam também. O acelerador atual foi inaugurado em 97, então a gente operou por 22 anos. A gente pode dizer que ele se tornou desatualizado há cerca de 10 anos, mais ou menos. Então esse é o prazo para você estar produzindo ciência de ponta. Depois você começa a ficar atrás e você tem que continuamente seguir fazendo upgrades na sua máquina, e foi o que a gente fez no VX. O VX, na verdade, não é uma máquina de segunda geração mais, ele é de segunda geração e meia, porque ele já tem alguns dispositivos que caracterizam ele como de terceira. Então, foram feitos upgrades para manter ele operacional e valendo a pena de ser mantido em operação até os dias de hoje. O Sirius é a mesma coisa, pelos primeiros anos, ele vai ser a máquina mais avançada que existe na classe de aceleradores Sirius, de synchrotrons, de 4ª geração do mundo. Ele está sendo feito para ser o mais avançado. Mas, rapidamente, outros aceleradores do mundo vão passar por upgrades e vão chegar na nossa cola e vai ser uma competição. E nos 10 anos a gente vai estar desatualizado.
Sim.
Isso é normal.
Essa é acho que é algo mais técnico, geopolítica, se a gente parar para pensar como está sendo feita a condução do investimento na ciência, por mais que a gente tenha essa infraestrutura, não quero nem pensar talvez seja um pensamento colonialista, mas eu acho que talvez seja muito fácil de um país da Europa assim superar nós, por exemplo, a gente está fazendo isso agora, só que tipo, se a gente não está sendo distribuído dinheiro para iniciação científica, está sendo cortado para mestrado, doutorado, qual é a perspectiva da gente se isso consolidar como um país de nível de ciência de elite, sendo que...
Eu não tenho essa resposta. É óbvio que aqui no Brasil a gente sempre tem que lutar 10 vezes mais para dar um passo para frente, né? Então é um sofrimento muito maior do que se você for num país como a Alemanha, que tem um orçamento muitas vezes maior que o nosso em ciência e tecnologia. Então, assim, as prioridades no Brasil são outras. O que tem acontecido, que a gente tem visto, é que, pelo menos por enquanto, o governo ainda vê os Sírios como uma prioridade nacional por ele atender várias áreas fundamentais da ciência e da tecnologia e de problemas reais da indústria e da agroindústria do Brasil. E a gente tem usado esses problemas de medicina, de agronomia, de geologia para vender o nosso peixe. A parte de medicina, é isso que impulsiona e que garante que a gente consiga manter um fluxo de caixa e de um orçamento funcionando, para manter a ciência básica. Claro que não é a origem da vida que paga isso. Não adianta eu ir lá para o Bolsonaro ou para o Pontes e falar que eu quero milhões para fazer experimentos de química pré-biótica para entender como que a fulgerita funciona. Não vai pagar. Né? A gente vai no rabo disso. A gente tem que usar a ciência aplicada para vender a ciência fundamental. Infelizmente é assim.
Fala que tem grafite mundial que dá tudo certo.
Questions?
I have one question.
Please.
I'm just curious about it.
So you give 2 examples about the fossilized fish and the rock things in the rock, 3D stuff.
Yeah.
So if I have, for example, a modern microbial lab, like it's soft tissue or whatever, can I do like a mapping of that too, or geochemical map? Because it's soft, it's impossible.
It's more challenging.
Yeah.
It's certainly more challenging. I had a student that was working with microbial mats, so we were keeping the microbial mats alive on the lab, and we are studying the precipitation of carbonates inside the microbial mat by mapping them. But what we had to do these studies for the moment, because we didn't have a cryogenic setup, we had to desiccate the microbial mat. So we lyophilize it and then map it. We lyophilize it, cut it, and then map it. But of course, when you do this, we induce the precipitation of other minerals, so which is a problem. The ideal would be to do it fresh or in frozen state. But that's something that we can't do nowadays. At Sirius, we'll be able to do it. In fact, we have already one collaborator there at the Mogno beamline, which is a CPU beamline, and we plan to do biofilms, to do 3D imaging of biofilms fresh. That's what we want to do. But we are also going to be able to do cryogenic studies. So for most of these high-resolution studies, we need to go cryo. I didn't even say it, but I was bragging about the high flux and high gradients and how beautiful that is. It's not so beautiful because you burn the sample. So you start to have radiation damage. You induce the formation or the destruction of molecules. So freezing the sample, we minimize this. So at Sirius, we'll be able to do the 3D imaging of fresh samples. We plan to do it. We already have a cell that we developed to keep the microbial mats alive, and we also be able to do the measurements in frozen state. So that can be done.
Any more? So let's think again, Dr. Dylan. So let's have one more coffee break and wait for you around 4:30.
In fact, I don't know, Chaco. What we have now is essentially some time for discussions and conversations on this topic.
Is it now or just after our break?
I want to hear about you. If you prefer, we could even do this during coffee break. If I had some wine, I would offer some wine. But I heard that we can't. But I think we could just do the discussion during the coffee break and see. In a more social environment. I think that's going to be better.
So somebody can just grab the coffee.
Yeah, even just talk about it.
Yes, your question is just
Well, guys, welcome back.
We should be closer together.
If you want to come closer, you participate more closely that way. The idea here is just to make some closing remarks on maybe what we have learned after these 2 days of talks. and it is to hear from you, maybe to lay out some rocks for us to keep stepping up on the understanding of the origin of life on Earth and on other planets as well, and to study the ancient life on Earth. So we are open, the floor is open for us to talk about, to discuss the ideas, to see what we can do in terms of theory, experiments, field work. What is next nowadays on the field of the origins of life and ancient life on Earth? So what we can do? I don't know the answers here. I would like to hear from you, in fact.
So perhaps I should start with a problem, which is that we basically talked about origin of life and all the different scenarios that are possible, emergence of life. Then people like me come up and say, well, the oldest fossils are already highly developed biofilms, ecosystems, literally. And those fossils are from the oldest well-preserved sedimentary rocks. They can have the green, what is this? Gosh, I'm blanking. What's the phase the metamorphic, the first one? Green schist? Yes. Green schist. Oh, I'm teaching them, I should know that now. And those rocks have a maximum age of around 3.48. The Dresser Formation, maybe the ones in Brazil are older, are they?
Yeah.
Yeah? Oh, good. So that's basically the stage where we find the oldest fossils, but at least until now the oldest fossils are all very highly developed biofilms. So now we have the problem, well, it can't go older in the fossil record. If we do honest science, we cannot go and find something. It gets really, really difficult. So now the question is, how could we approach the question of emergence of life? And in fact, all we can do is lab experiments and maybe modeling, things like that. But we really never will be able to prove what we think could be in the fossil record on Earth. And maybe we can do that on Mars in the future by taking a look at rocks that are significantly older than those on Earth, but that were laid also in an aquatic setting, and they are not metamorphosed and pretty fresh, because on Mars, as far as I know, weathering doesn't really take place like on Earth. So that we basically tell, well, here are our ideas how the earlier life may look like, that we have not recorded on Earth, but this is what we might want to look at on Mars in the appropriate settings. And I have no overview right now whether we know enough already on the ancient environments preserved on Mars. I know right now the Jezero crater is a delta, a river, and so forth. So that maybe we and a future generation can go and really target certain environments and look for certain signatures that might be significantly different than what we have until now on Earth. So just like a general approach, strategic approach. Does this make sense?
Well, why would it be significantly different?
Yeah, so I like what Evelyn showed in her talk, where she said, well, we have the domains of life, like archaeobacteria and so forth, but she said, well, in the Archean, it's a network, so it's not a tree of evolution, it's a network of so we really don't know, what exactly was there.
But the network was a biofilm.
Well, the biofilm is already advanced if you think of how complex that is.
I think that we shouldn't. I think there's an error of thought here, if I may say so. That is that any emergent system has to emerge rapidly, otherwise it doesn't survive. So I would argue that when I say 10 to the 21 nanoseconds, we've got to really try to think in the nano world. And if you think about the nano world, the first stop that we call life is going to be a bacterium and archaea probably, and that'll be very fast. So I would say it's better to look, well, I think it's better to look from the bottom up, because I would argue that were you to find life on Mars, then, which it does worry me there's no iron formations on Mars, but if you were to find it, at 4.3 billion years, it's going to look very much like it does at 3.5 and 3.7. So, because that's the organization of life. It's doing the same job, all the time doing the same job. And of course there's a lot of gene transfer. I think that was one of the points about that. But nevertheless, these things are cells, and they're always about the same size. They're always doing metabolism. Basically, it's always carbon dioxide at the bottom, just like it is today at the bottom of the food chain. Right at the bottom of life, there's no doubt about it. I think that it was carbon dioxide. And they were basically autotrophic. They were not heterotrophs.
Yeah, no, what I meant
you would run out of breakfast and heterotroph.
Yeah, what I meant is anything before the first cell, because a cell is
We're
already...
never going to find that, because that will all be dead, all gone. I mean,
Now, well, if there are fossils, they're gone anyway, right?
well, there's, it's going to be a small amount of prebiotic material, if you want to call it that.
Yeah.
Probably cellular anyway. And it's going to just be eaten up by whatever's coming next. And it's got 10 to the 21 nanoseconds is about 160,000 years. It's a hell of a long time if you're trying to make life. It's enough. The emergence of life was rapid, really rapid. And then you can think about the long drawn out Darwinistic kind of evolution. But if you don't get to the first cell within 10 to the 21 nanoseconds, you don't get there. It's not slow. We are in a nano world here.
But this
We're
first
a
cell
pico world, really.
this first cell can be something very simple, right?
No, it can't be that simple. It's got to be relatively complicated, because it's got to be able to do the acetyl-coenzyme synthase pathway. It's got to be able to do that, because that's how, it seems there's no other way, as far as I know, to make CO2 into organic molecules in the acetyl-coenzyme synthase pathway, and that's right down the bottom of the evolutionary tree in both the archaea and the bacteria.
So you basically have an explosion-like kind of thing, and then you have life like super fast radiating. So you would have, if you would take a look at the rock succession, you have rocks completely, just physical, chemical rocks, and then suddenly something completely new. Well, then it would be important to find this boundary on Mars.
Yes.
So, and that's what I mean, you need to see that somewhere in the rock record.
Probably not, because supposing you have a life starting. I think a lot of people now will agree that it could not have been at the surface for lots of different reasons. So it's probably down on the seafloor somewhere. Say it's an alkaline vent. The ocean is a desert. They will never get out of the ocean. The idea that these bacteria, whatever they are, protobacteria, will get out of the vent and then kind of find out what it's like to live in the ocean is hopeless. The only chance for life to evolve from an alkaline vent is in what we call a deep biosphere. Not that deep, but deep. It's got to be on the ocean floor and just beneath. Because at the bottom of the ocean floor, now and then, is very similar to what it's like at the alkaline vent. So in other words, your real evolution, why it has to get better is because it's left the womb of the alkaline vent, and it's kind of got to live in a similar situation where the chemistry is extremely similar, but much lower disequilibrium, much lower content. So that you have instead of got 100 millimoles of hydrogen and, shall we say, 10 micromoles of nitrate, you've suddenly got much less and much less, and also you're probably looking for another electron acceptor apart from nitrate. But I would say, I'm pleading, I guess, that what the synchrotron can do, which by the way I think it's extraordinarily exciting, and I've lived 15 years in America, and I am relieved to see something like that happening here, because my worry is that actually America is not going to do much like this anymore. Big statement, but nevertheless, I'm worried about it. So it's fantastic to see this. So why not look from the bottom up? I mean, look absolutely from the bottom up. And I agree with you, it's got to be an engine. It's got to be an engine. Because everything that emerges in the universe is an engine. So why not life as an engine? And that's what Galvani said 225 years ago. But we seem to have forgotten it. So let's have a look at something like pre-rust. I'm not saying this is right, but that it really does change confirmation as it does stuff. Something you can look at on the synchrotron.
And that's what I meant. And the green rust is not a cell, right?
Well, it depends how you think of a cell. I mean, you can have a cubic cell.
It acts like some
yes, it's
not
got
an organic cell.
And
that's what I meant to look for.
It has water on the inside.
Yeah,
it's got quite a lot of water on the inside, in, shall we say, 30 layers. And of course, as soon as something's happening in one layer, it's going to interact the other layer. So it's got to have the self-organize because of the boundaries of that it's given to you by the green rust. So you can actually make predictions. Once you've got one thing going, you can make predictions about what might be next because of what's happening in the other. So if you've got something like that happening in one layer, then it's going to have an effect in the next layer and so on.
So what you could, maybe we should change and don't use the name cell, but use the name organized water, a pattern of organized water somewhere.
It's compartmentalized.
And then
there's another way of putting it, and that is it's compartmentalized compartments.
Yeah.
You've got a green rust, and it's got compartments in it.
Yeah.
Lots and lots of them, just like a cell.
Yeah, and then you have to compare that on the background sediment that you have in order to identify whether those patterns are repetitive somewhere, in variation maybe, but that would be a good start to do, and that's basically what I meant to say. If you go on Mars and then we look for something, we don't know how this very early life looks like, but all we can do is look for patterns that are clearly different from the background sediment, measure that, and hope that at some point we find something which is not yet a real biofilm, because I think a biofilm is on Earth, but we don't know on Mars.
Otherwise, how do we get started? We all need it.
Good.
I think that very interesting.
Hello. I think a problem we need to solve is the problem with biogenicity, how to test biogenicity. I think it's always going to be a problem, no matter which age, no matter how old is the fossil, even being an Archean fossil, we always will have this problem. We can see this, we are just talking about that during the coffee break, because people publish articles with tracing about the Archean life, and then another group publish a reply saying, oh, that's not life, that's not a fossil. So I think we are in a constant looping, or I don't know how to represent it, but always making circles, never. I think we need to make very clear the biogenicity studies and maybe come from the present to the past. So using, promoting experiments with modern life, fossilizing them, understanding how they are preserved, and try to, clean this aspect of fossil record, of such an ancient fossil record. I hope I make myself clear. I'm sorry, my English.
And the most important thing is if we do like lab experiments on something, like let's say fossilization, lithification of organic matter, we always have certain parameters in the lab to run those experiments. And because we don't know early Earth, we don't know only very little, let alone on early Mars, we don't know nothing. I mean, we don't know nothing, yes.
Not necessarily. I think we know an awful lot.
Yeah.
I just don't accept.
Yeah, but the thing is that, so instead of running specific experiments to say the pirate forms under those and those and whatever, it would be better to really analyze what are the principles of taxonomy so that we have a pathway that can be adapted to different situations. And that's physics and chemistry, and since I don't know physics and chemistry, I will not talk any further about that, but those are just normal thermodynamic processes. It's nothing in there anything, that's decomposed, that's what it is. And I think that's what I wanted to say.
Yeah, and understand it in the different levels, since the millimetric level to nano scale. To nano scale. So we can go further into the Archean and Hadean, try to look for this very early life. So,
Yeah, for instance, the image that I showed there, from the gunflint formation, when we started studying it, this comes from Link Mountain, from the gunflint formation, and this is very well described fossils preserved in hematite. So we expected to find hematite, and we found that yellow mineral in there, which had the appearance of hematite, but it didn't have the density of hematite. And what we learned by going to the nano world, to the nano resolution, is that inside the cell, it wasn't hematite, it was magnemite, in fact. And we showed this by Raman and by magnetic measurements with Ricardo Trindade, that it was magnemite. So the taphonomic pathway was different, so hematite was, in fact, transformed. So it's something completely new. I think the biogenicity, there is a lot to be learned, especially when we go to the nano, and we need to learn about the mechanism. I agree with that.
Yeah.
It's a long way to discuss this. If you want to discuss when we get the samples from Mars, and if you want to discuss if this is, if we have biological signals there, we need to learn more about the taxonomy.
Yeah, in many processes, I think, I'm not a nano expert, the nano world just functions differently than the microscopic world. So like, for instance, if you have a microbe and it's very, very small and it's floating in the water is actually highly viscous because the particle, the microbe is so small. So that means certain processes that we might observe in a bigger cell under the microscope, on a thin section with water, whatever, that doesn't work anymore. And I don't know how far the research is done in things like lithification in a nano scale.
That's where it's at. That's exactly where it's at. The nano scale.
Yeah, but I don't know if anyone's actually worried about the mechanism and how it's working. I know Frances Westphal is doing a lot of work with lithification, but I don't think she's actually measured the minerals that are being formed on the nanometric scale. I don't think we are worrying about that yet. I know that Flavia is slightly interested on doing nanopaleontology, and she studied the precipitation and the organization of minerals on the nano scale. And I know she's going to do some measurements soon with some very interesting samples, right? So it's something that can be done. Sorry, Gustavo.
Just a comment on Nora's proposition. It's perfectly viable. Preservation conditions on Mars, they are not perfect. There is some erosion. In the past, there was even more, like water erosion and wind erosion and other geologic stuff, even ice erosion, glacier erosion. But the next NASA rover, due to launch next year, is going specifically to a place in which conditions for past water and sedimentary material is really strong, it's very compelling. And it's going for sample return in the future. The rover is going to collect to make a cache, and sometime in the future, the next mission is going to collect this cache. There will be geological context, there will be imaging, and between, if I remember the numbers, between 10 and 20 kilograms of rocks. It's pretty respectable, yeah, for our first sample return. Sample return is the next natural step. So I was a kid when the Viking actually landed on Mars, and 40 years have passed, and there has been no astrobiological experiment of any kind, anywhere, in any probe. So they are trying to do it again, but not looking for life, or signs of past life, or evidence, whatever, with geological context. I think it is very sensible.
This is one of the reasons that we need to better understand the criteria of biogenicity and improve these criteria and exploring the nanoscale, because we don't know about the nanoscale.
Yeah, and then there's another thing, if the fossils are very old and the rocks are old too, That's the aging process. So even if in the lab, and I know that because we were trying to fossilize microbial filaments, so we created tenorite, and then the tenorite crystallized into pyrite, or the early, I call it amorphous aragonite, which is kind of a joke because a mineral is crystalline, right? It's not amorph really. So, but it was an amorphous aragonite, and it crystallizes into a crystalline aragonite. And as we all know, aragonite is not stable. It wants to become a calcite. If you think of a fossil in a rock sits for 3.5 billion years somewhere, this enormous time affects the crystallinity and the mineral chemistry as well, let alone things like hydrothermal alteration and there's so much more that happens. And there I think at some point you run into a wall because we can't sit for 3.5 billion years at our autoclaves and wait for our sample to age, but maybe we can do some math and modeling and so forth to yeah, at least theoretically approach that and then say if we have a nano-type organism, how does this look like in a really mass rock? You know, what's the alteration and hope for the best, yeah.
I have a question for Evelyn and Nora. What's your opinion on the microfossils from Mars, the Allen Hills meteorite? Remember the ALH840001? What do you make of them? Are you believers?
I turned it off.
And I let her first talk because I don't know nothing. Really, I have no opinion on that. I know a little bit. And what I know, I think they are pseudofossils. Pseudofossils. Yeah.
There's not enough room for the DNA in them.
We see some important aspects that missing important aspects to conclude their past life.
There's no compelling evidence.
What we found there that form the pseudofossils. No.
But I think there is still some discussion on the magnetite that was found on the Allen Hills meteorite, isn't there?
I don't know.
Flavia. The magnetite discussion of
Well,
Allen.
there's a magnetite discussion that it could be granite, the magnetite in granite, but you know that the Allen Hills, I mean, that whole story was most unfortunate, and I do think that's where you need to know kind of the politics of what was going on at the time. They never meant to release it as life like that. You probably know, I mean, I don't know if you know the story. Do you know the story? I mean, basically, some guy who worked for the White House heard that somebody discovered life on Mars, and he told his, what's the good way of putting it? Anyway, his bedmate that night, and she phoned the New York Times in the morning, and out it came. And meanwhile, the President Clinton, I think it was, and was worrying because what are we going to tell the Pope and so on. There was a whole lot of trouble about it, and so in other words, we heard about it way too early. So, and I think we might, I mean, there's many people who worked on microprobes at the time, looking at things like gold, and they would have known that that was a pseudofossil, because it's just a self-organized pseudofossil, and it probably, you know, might be, at least in the kind of work done on this planet, was an actually effect of the analyses. Now, I'm not saying it's an effect of the analyses on the Martian meteorite, but you just can't get enough DNA in there, or any DNA. It's just too small. So it's, you know, it's nonsense.
Yeah, I can tell about the magnetite. This meteorite is rich in magnetite, and there is an article, I don't remember who is the author, but they tested the biogenesis of the magnetite. And the magnetite contained, no.
Well, Busek, I mean, are you talking about Busek or something you wrote against Busek? Busek was the guy who started thinking about whether this could be greggite or not. His conclusion was no, it was not. It was not originally for a magnetic bacteria.
No, they compare the magnetite containing the meteorite with the biogenic magnetite, the magnetofossils inside the magnetostatic bacteria, and they test inorganic magnetite. And the magnetite in the meteorites is almost the same thing. They have almost all the parameters of the inorganic magnetite. So I know about this.
I don't know, what about Europa? Because we're talking about Mars, but Europa is a place where we have chemical disequilibrium, right? We probably have hydrothermal vents, hydrothermal systems. What's your opinion? Do you expect us to find any signs of life?
Is it still being going on the web? Have a beer sometime.
Okay, tonight.
I mean, if you want to read a paper about it, the best paper on this is we wrote a paper in astrobiology last year or the year before on the possible life on the road. Difficulties are, as usual, the oxidants. So of course, because of the radiation, the high electron radiation onto Jupiter's surface, you could say there's oxidants in it. Then you've got the trouble of getting through 10 kilometers to 30 kilometers of ice. Now, people at times started to say, or did say for a while, that you could have plate tectonics associated with the Europa ice. But I mean, there's nothing to suggest that any body force that would really turn it into a really convective system. So that you've got to, otherwise, how do you get the oxidants down into the subsurface? If you do, then the life will be, the biofilms will be absolutely on the bottom of the ice wherever there was a crack that the oxidants came down. Because as I said yesterday, it's like trout in a very hot summer's day. They're looking for the oxygen, they're looking for the waterfalls. They've got to get oxygen. So it will be the same with the bacteria. They've got to, of course there's no oxygen, but they've got to find the nitrate or the sulfate to be able to breathe. They've got to get rid of their electrons. So it will be just underneath, actually probably attached to underneath the ice. So that's going to be quite hard work finding that. But there is something called the Europa Clipper, which is going to go around. I think that unfortunately the actual drilling one, what I've got recorded, I know I was on that particular board, but worked on that possibility that you go down and drill a little bit at least onto the ice. But
it was cancelled, right?
It was cancelled. The Republican, the irony is, it was the Republican Texan that was pushing it, and he lost to a Democrat. So, whose side am I on?
I would like to propose the discussion of one concept. I don't know if you could talk about this, or Mike, or any of the pedestrians, about the Fermi paradox. It relates to what we were talking, but it would be, there was this Italian astronomist, I think, and then he researched about and elaborated formula. I think it's Drake's formula. I don't know. It's another scientist to level the. If we find a extraterrestrial society, what would be the level of intelligence? But by what we are talking about here, I have understood that it has been kind of comprobated already. Extraterrestrial life exists as in form of bacteria. No, this would be the second question. What people have talked here about eukarya, archaea. I'm not a biology specialist, but what about the bacteria that comes in probes that go to space? Not necessarily to that land in a specific planet, but I have read about bacteria and microorganism lives, type of life that returns in NASA probes or SpaceX. I don't know. Would be these two types of things. Is it extraterrestrial life? It hasn't is it comprobated? Like, if you these beings, bacterial beings, like type of life, have been found in space, can be considered life. And if you can find a smarter type of society, right? Maybe there.
First question. You made a lot of questions.
Family
paradox.
Se existe porque a gente ainda não encontrou.
I think the best recent analysis of this is to Paul Davis, his book,
The eerie silence. Eerie is a word that's difficult to translate to Portuguese, but something like strange or chilly or uncomfortable.
Silêncio
In Portuguese, eerie, E-E-R-I-E. It's a word that does not have a quick translation to Portuguese. His analysis is pretty simple. I think he made a really true job of nailing down all the premises and all the stuff that's really going into the Drake equation. And his conclusion is not very optimistic to us. If civilizations do exist, they don't live very long. They may be numerous, but they don't live very long. They get extinguished pretty fast. That's what the numbers are saying. He's a physicist, actually a cosmologist by training. I tend to agree with him. It's a very small book, a very nice one. I recommend it to you. I'm not sure it has been translated. I don't think so. So, this is where we stand right now with the Drake equation, I think.
Is located on a very far galaxy from us. I don't know, this seems like sci-fi.
Yeah, he's using actually Carl Sagan's numbers. He uses the Carl Sagan analysis as an input, as a starting point. The numbers always kind of boil down to if we are not observing in really convincing quantities, they gotta be short-lived. Whatever you choose to adopt, say, as level of intelligence or technological achievement, the numbers suggest that civilization are short-lived.
Well,
so we shouldn't worry about it.
Because we have done our entropic job. We've taken all the coal and iron ore and so forth and distributed it, so to speak, as pollution everywhere, and that's it. And it could never happen again. It's just inevitability of entropy generators.
Maybe it's preposterous to, I don't know, I think
maybe it's, I don't know if it would be arrogant word or preposterous, but like it's kind of egotistical to believe maybe it is and maybe it's right, maybe it's not. That's the real question, but yeah, maybe Earth is the only planet out of a billion, I don't know, on the whole universe, and only us are intelligent beings, or not, or we are, or that is a wrong idea.
Consciousness is an automatic, I would say, evolutionary part of life, and it would probably happen with the dinosaurs if we hadn't had that big Jack's-Love impact. So basically, consciousness can mine the fourth dimension. Well, you can do that very fast. So that's the unfortunate. By the way, I have 8 grandchildren. I don't think I'm not highly concerned with the future. But the idea that that any civilization would last, should we say, 10,000? Well, technically, kind of civilization would last a million years. It's just, I mean, most the biologists will know what's a normal species lifetime.
1 million years.
1 million years. So if we do it much faster, so it's much more likely 100,000 years.
And you're not factoring in technology and expansion.
Even with that, because everything costs more.
So the quantity of resources, say, take,
yes, but
what's his name again? That guy who was talking about asteroid mining. He calculated that the quantity of resources, mineral, water, whatever, in the asteroid belt alone would support 1,000 times the population of the Earth.
No, but that's not the point. The point
Even if
is,
a tiny fraction of that.
that's not the point. The point is, I was about 30 when the Club of Rome report came out in 1968, I think it was. And their point was, of course, we're going to run out of materials. Okay, maybe we'll find new ones, but you're never going to solve the pollution problem. You're never going to solve the waste problem.
This is very pessimistic.
It's very pessimistic. Well, okay, so it's up to us to try and think of ways to do that. So I don't want to be pessimistic. I can't be pessimistic, but we're not talking about that kind of thing now. We're talking about looking for life in another universe. It's going to kind of use telescopes to find us, and we're going to find out. I mean, that's ludicrous. It's hopeless. And the Drake equation really is over. We don't have to think about the Drake equation. We just have to think about the appropriate disequilibrium on the nearby stars and
On an optimistic note, say we consider the recent data from exoplanetary researchers and all the satellites, not the data. The data suggests that the average star in the galaxy, a low-mass star like the Sun, probably each one of them very likely possesses one habitable planet. That means at the right distance and so on and so on. That means for hundreds of billions of potentially habitable planets in the Milky Way alone. I'm not an optimistic, but...
No, but you've got to have the right depth of an ocean. I mean, the fact that we've got dry land is pretty extraordinary, I would say. You know, why do we have an ocean as deep as Europa, for example, or no ocean at all, like you pointed out? I mean,
I agree with you, yeah. I agree.
Dolphins cannot make telescopes.
Anyway, the next generation, St. James Webb and perhaps new coronagraphs and the next generation of ground telescopes, they probably will be able to survey, as I showed, nearby stars and look for photosynthetic signatures in potentially habitable planets. If you say you look at 50 planets and you don't see shit, that's it, that's the statistics. Yes, you have something to talk about. We looked for life in 50 planets and found nothing. That's something.
We should get back to what the fantastic things going on here with the possibilities of the
I would like to raise another kind of question. If there's no one
there was one final question, I guess. He asked if there is any actual sign of extraterrestrial life ever found. Already. We talked about Allen Hills, pseudofossils. They're bullshit. Okay. But we have the other option here, which comes from Nora, who found something on Mars. And so she has the idea of finding MISS, which is a microbial-induced sedimentary structures on Mars. She has published that.
It's thermofibers.
We don't know. We don't know. And maybe Nora can talk a bit more about that work, specific work.
And you might want
if we should believe in you, maybe.
You might be very careful if you say, detective life from Mars. Let's say what it exactly is I took a look at the publicly available photos at the JPL webpage. After having a discussion with someone at JPL, I should do that just for fun. So I did, and I was not funded, I had time. And I detected morphologies on photos that resembled strongly MISS. So I wrote this paper. This is an observation, and it's just an observation and a suggestion that it could be perhaps something like a microbial mat system. But I also pointed out in the same paper what else it could be and what needs to be done in case someone sees something like that on another planet, so all the series of analyses and so forth and so forth. What I meant to say is that if you look for life on another planet, looking for biofilm textures and structures, not necessarily for an in situ preserved fossil or something like something with carbon, might be an avenue to try, especially if a planet is terrestrial and has a lot of classic material. That was all I wanted to say in my paper. Very careful.
It could be after physicists and not the astronomers. Is the carbon dioxide on Mars collected, so to speak, recently, or is it actually an excretion from the planetary interior? Say it again. Is the carbon dioxide on Mars, is a small amount of carbon dioxide on Mars kind of intrinsic to Mars and its geochemistry, or is it just an addition from comets?
It's very likely primordial.
Primordial.
Just like on Venus and the Earth.
And
And
how
the
much-
total amount, of course, must have differed in geological time, but it's pretty certain that carbon dioxide was there from the very beginning, in all three planets.
So why isn't there much carbonate, or almost any carbonate on Mars?
Okay. Mars does have some carbonate, but
Yes.
it's really very, very rare. And
Very
I'm not a geochemist, I'm not a planetary scientist, I'm a stellar astrophysicist, but I know that people think that a possible explanation for the near absence of carbonates is that the oceans were probably acidic, and that would complicate
Yes, but
the
eventually,
position of
yes, but
carbonate.
eventually when they evaporate, you're still going to have to precipitate that.
They are there, but
So I would say
Yeah.
that's a real puzzle, why there isn't carbonate
Yeah, it
to speak
is.
of on Mars. And
there are lots of sulfates, but very little carbonate.
Yes. So if there's no carbonate, or very little carbonate, and not much CO2,
But there are possible explanations. Say, I know nothing about this stuff. I just read some papers. They say that some volcanic action, depending on the quantity of sulfates, might really have neutralized the deposition of carbonates. I might say something silly because I'm really not a geochemist, but I read the papers. That's what the guy is saying. If you inject a lot of sulfate, you can essentially make carbonate deposition rare or difficult. Something like that. What I'd like to propose is a sociological question following you. Is that I have been talking about astrobiology for some time now, more than 20 years. And I used to tell my students and people, say general public in the beginning, that when we find the pathetic bacteria on Mars or something like that, that's going to be a revolution, an epistemological revolution. First page in every newspaper, they're going to stop the soccer championship. Now, I think if we do find something that's published, refereed, etc., no one will give a damn. People will say, how come? Haven't NASA found life on Mars like 20 years ago? That's what I'm talking about. Of course there's life on Mars. I think the perception of the society of people has changed. Maybe I'm from the Star Wars generation. I watched the first movies as a kid on the screen, on the movies. And people, the way people think about this changed. It really is kind of, there will be no real surprise. Nobody is going to be impressed with this. Oh, life, extraterrestrial life, of course, why not? Yeah, we just got invaded last week by some sort of civilization. People really in this information era, I think people will not make the right connections. They're not connecting information, science, knowledge is no longer the currency. The currency is information, it's the web. So I think people is really, they're going to gloss over this. What do you say?
well, I mean, the sociological answer to that is that we now live in what's called the cargo culture. Now, if you don't, and I don't want to go into the cargo cult, but if anybody knows, so if you don't know about cargo cults, I'll say what they're very quickly.
The islands,
So cargo cult is, I mean, I'll give you an example in the Solomons.
You're talking about John Fern religion.
I'm talking about the fact that in Guadalcanal, which we both know of, that what happened to the Guadalcanal people was in 1940, big birds came in from the sky, and they had lots of chocolate, and I'm not being facetious about this, chocolate and chewing gum and stuff like that. And that was because they chopped down a whole lot of trees. So once they chopped down the trees, then in come the birds. So the cargo cult was run by chiefs, certain chiefs in the tribes, various families in the Solomons, insisting that the people cut down trees so that the cargo would come. Now, we used to, I wouldn't say laugh about this because we were there and we had great empathy with them, but the fact is that's how we live now. It's a cargo cult. We don't know how anything works, nothing. We just buy it off the shelf or listen to it on the radio. We're not thinking anymore. So I suddenly realized, I could watch steam engines work. You can't see how things work anymore. So the kids don't know. There's nothing to show them how anything works. It just is there. Thank you very much. Give me another $20, baby.
Maybe that's why
Civilizations don't last very long. They reach a cargo culture and they just go extinct. They forget how to make stuff. They forget how to interpret nature. They forget how to
They
think.
get run over on the road because they've got their earplugs in.
That's not a nice thought.
It's best to know.
So maybe what my personal opinion is about life detection on another planet, that it might be very similar to what happens on Earth with people who work on earliest life on Earth, where we have reports about, oh, this could be a fossil, and oh, I have the biggest, oldest fossil, and look at my fossil, and no one is really convinced that those are real fossils. But there are a lot of individual reports of things that could be, and it makes sense, so that actually we have not like the one big super report that changes our view of the universe, but many little reports about some things, simply because there is this gap that we cannot really prove anymore. Was this life? Because there's just no bridge anymore. That's all. Different planets. It's a long time ago, and it looks different. We really have no model for that on Earth, perhaps. So that it's more like a wave of reports, and then it's dissipating a little bit, and there's no real super fun.
Can I give you something optimistic? You're always asking for optimism. Okay, so astrobiology, it happened, and a lot of people were extremely cynical about astrobiology, and are to this day. But actually what happens was that it actually gave us, for the first time, a good excuse to be transdisciplinary. So it has made an incredible cultural impact around the world. And none of us, I thought that would happen. We had no idea that would happen. Because everybody says astrobiology is not a discipline. It's not a discipline. No, it's not exactly a discipline, but it's a transdisciplinary field, and that's wonderful. So here we all are together, from physics and chemistry and geology and biology and zoology and so forth. It's just extraordinary in that one way. So I think that's very optimistic, intellectually.
I appreciate it.
Okay, so anyone want to add something? If not, I would like to invite you all to continue the talks and the discussions by having a caipirinha on the hand. So we're going for a bar. We're going to Bar dos Juarez. If you want to go with us, you're all invited.
Really?
Yes, we're going to Pinheiros.
Now?
Yes. Directly off to the bar.
Be optimistic. Come on, it's
We can have fun and keep the discussions on about the origin of life and the future of life. Okay. And that's it, guys. Thank you very much for your participation.